Hey everyone, and welcome. If you're getting ready for your CBSE 2026 board exams, then you have landed in the perfect spot. Today, we're going to break down one of the most, fascinating chapters in all of physics, wave optics. This is your go-to guide for crushing the concepts and acing those exam questions.
So let's just jump right in with the big question, the one that had scientists scratching their heads for centuries. What is light, really? Is it a shower of tiny particles the way Newton imagined, or is it something completely different? This is the central mystery that wave optics is all about solving, and it does it with some seriously clever experiments. So here's our game plan for today. We'll kick things off with the core idea of light as a wave, and then get into how Huygens' principle explains its every move. After that, we'll hit the superstar of the show, Young's double-slit experiment. Then we'll explore diffraction and polarization. And to wrap it all up, we'll put together a board exam blueprint just for you. All right, first things first. The absolute core idea of this whole chapter is that light acts like a wave. So for now, I want you to just forget everything you know about particles. Instead, picture those ripples spreading out in a circle when you drop a stone into a pond. That's the picture, that's the model we're going to use to understand everything else. Okay, so if light is a wave, how on earth do we predict where it's going? Well, a brilliant scientist named Christian Huygens figured it out. His principle is basically the official rulebook for light. It tells us exactly how a light wave travels and spreads out.
Now, to really get Huygens' principle, you first have to understand what a wavefront is. Let's go back to that stone in the water. A wavefront is just like one of those circular ripples. It's a line or a surface where every single point on it is doing the exact same thing at the exact same time. We call that being in constant phase.
And here's the magic, broken down into 3 easy steps. First, imagine that every single point on that wavefront is like a tiny new light bulb, sending out its own little waves. We call these secondary wavelets. Second, these little wavelets only move forward. And third, the new wavefront, where the wave will be a split second later, is just the surface you get by drawing a line that just skims the front of all those little wavelets. That's it. That's literally how light gets from point A to point B. And now, for the main event. For a long time, the wave theory was just that, a theory. But then, along came Thomas Young and his famous double-slit experiment, or YDSE as you'll see it. This was the experiment that provided the undeniable, rock-solid proof that light behaves as a wave. And you guessed it, it is an absolute favorite for board exam questions.
But hold on, before we look at the results, there's a catch, a really important one. The experiment only works if the light coming from the 2 slits is coherent. Now, what does that mean? It means the light waves have to have the exact same frequency and a perfectly steady phase relationship. Think of it like 2 drummers hitting their drums in perfect, unwavering sync. Without that perfect timing, the whole effect just disappears.
Okay, this right here is the mathematical heart of it all. When the waves from those 2 slits finally hit the screen, they interfere with each other. They can either build each other up or they can cancel each other out. If the difference in the distance they traveled, the path difference, is a whole number of wavelengths, n lambda, they sync up perfectly and you get a bright spot. But if it's off by half a wavelength, n plus 1/2 lambda, they completely cancel out and you get a dark spot. And all of that leads us to this super important formula for something called fringe width. Beta, or beta, is just the distance between 2 bright spots or 2 dark spots on the screen. And what this formula tells us is that the width of those fringes depends on the wavelength of the light, lambda, how far the screen is, d, and how far apart the slits are, d. Trust me, this formula is going to be your best friend for solving problems. But wait, there's more. Interference isn't the only cool trick light waves can pull off. What do you think happens when a light wave hits a really sharp edge or squeezes through a super narrow opening? Well, it actually bends around it. And that phenomenon has a name: diffraction. Now, it is so easy to mix up interference and diffraction, so let's put them side by side. Interference happens when waves from 2 different sources meet. Diffraction is about waves from different parts of the same wavefront bending and interfering. The big giveaway, when you look at the pattern, is that with diffraction, that central bright spot is huge and way brighter than the others. In interference, all the bright spots look pretty much the same. We're almost there. The final piece of this wave puzzle is called polarization. This is a big one, not just because it's used in things like 3D movies and sunglasses, but because it gives us the final, ultimate proof of a really fundamental property of light waves. So what exactly is it?
Well, light is a transverse wave. That just means it vibrates in all directions perpendicular to the direction it's traveling, kind of like shaking a rope up and down, side to side all at once. Polarization is like feeding that shaky rope through a picket fence. Only the up and down vibrations can get through. It's all about filtering the light's vibrations down to a single plate.
Okay, let's switch gears. We've gone through the concepts, so now let's get practical. Let's build your blueprint for the board exam. This is the stuff you absolutely, positively need to zero in on to get a great score in this chapter.
First up, the non-negotiables. These three formulas right here. They are the foundation, the key to solving almost all the numerical problems you'll see. The conditions for bright and dark fringes, and the fringe width formula. You've got to write them down, practice with them, and know them by heart. No excuses.
All right, next, derivations. Oh yeah, CBSE loves to ask for these. You absolutely have to know how to derive the fringe width formula, beta, right from the beginning. And you've got to be able to use Huygens principle to prove the laws of reflection and refraction. The best way to learn these is to just practice writing them out step by step until it becomes second nature.
And finally, let's talk concepts. It's not enough to just memorize formulas. You have to get the why behind it all. For example, why can't you just use 2 regular light bulbs as coherent sources? Or what happens to the fringe pattern if you do the whole experiment underwater? Thinking through questions like these is what separates a good score from a great one.
And we'll end with this little thought experiment. This whole chapter has been about proving light is a wave. But you probably know from modern physics that light can also act like a particle. It's called wave-particle duality. And it just makes you wonder, doesn't it? What else out there in the universe is living a double life? And that's a question that takes you way beyond your exams, right to the very edge of what we know about physics. Keep asking those questions.